Now let us see, children, stereochemical aspects of this nucleophilic substitution. We saw briefly what are the different types of reactions that alkyl halides give. Let's go into details of nucleophilic substitution. Now we saw about SN1 and SN2 reactions. SN2 proceeds with complete stereochemical inversion, whereas SN1 proceeds with racemization. So we have to understand now what is meant by racemization. So first of all, let us see what is optical activity, and then we will go further. So now here, what is optical activity? See, this is ordinary light. When this ordinary light is passed through a special kind of prism called Nicol prism, which is nothing but calcite. Calcite is nothing but calcium carbonate. When it is passed through Nicol prism, then it becomes plane polarized. See, here the illumination is there in all the directions. But when it is passed through this Nicol prism, it becomes plane polarized. It gives illumination only in one plane. Okay, so you call it as plane polarized light. Now this plane polarized light, if it is passed through an organic substance, either it may turn towards the right or it may turn towards the left. Okay, so towards the right or towards the left. Now, depending upon to which direction this organic substance is shifting the plane polarized light, decides what kind of isomer it is. Okay, so that is called as optical activity, or the substance which is rotating the plane of polarization is said to be optically active. Okay, the substance which is rotating the plane of polarization of light either towards right or towards left is said to be optically active. Okay, now if it is rotating it towards the right, then this substance is said to be D isomer. Okay, yes, here you see it is D isomer, and if it is turning towards the left, then it is called as L isomer. Levorotatory, dextrorotatory you call it, and the substance is said to be optically active. Okay, now in order to show this optical activity at the molecular level also, there has to be certain conditions. Now what are these conditions? The molecule should possess molecular asymmetry. It should possess molecular asymmetry. What does it mean? It means that the molecule should have a chiral carbon. Now what is meant by a chiral carbon? Chiral carbon is that carbon which is surrounded by 4 different groups around it. Then it is called as chiral carbon. Like this. Here you have carbon surrounded by hydrogen, hydroxyl group, methyl and carboxyl group. So this carbon is said to be a chiral carbon. It is asymmetric from all sides. Now, number 3, the molecule should form a non-superimposable mirror image of itself. This is another condition. That is, the molecule, say for example F, if you show it on the mirror, it will appear like this. Same way B, you show it on the mirror, it will appear like this. But if you show A, it will appear the same way. So here you consider this as symmetry. That is, the mirror image and the object, if you keep over this, then you will find that they are overlapping with each other. There is symmetry. Whereas if you keep the mirror image over this, then it will appear like this, is it not? Then it is molecular asymmetry. Same way F, if you place it over this, now these 2 lines will be this side, is it not? It will not overlap. So this is called as molecular asymmetry. Same thing here. I'll give you another example here. So this is the example that I have given you in the previous. Now look at the mirror image. Here you will find OH on the left and hydrogen on the right. Okay, just the opposite. Now this is the mirror image of this molecule. Now if I take out this and place it over this, then hydrogen will be over this OH and OH will be over this hydrogen. So they do not overlap. Such images are called as non-superimposable mirror images. Okay? And if a molecule is forming a non-superimposable mirror image, then it is said to be optically active. Okay? And the pair of isomers, that is the object and the mirror image, they are called as enantiomers. Okay? Now, we have to understand a little more. And so we go with the simplest example, that is glyceraldehyde. This is glyceraldehyde. This is 2-hydroxy, 2 and 3 position they are having hydroxyl group, and there is a aldehyde group. Okay. Now try to understand like this: CH2OH, CHOH, CH2OH. What is this? This is propane triol. Okay. Whereas here 1 CH2OH is now here as aldehyde. Okay. This is commonly called as glycerol, and this is called as glyceraldehyde because of the aldehyde group. Okay. Now this is an asymmetric carbon, and you see the mirror image, it will be like this. So this will form a pair of enantiomers. This is called as D-glyceraldehyde. This is called as L-glyceraldehyde. Now what is this D and L? D and L tells you the position of OH group to the asymmetric carbon. If the position of OH group is to the right of asymmetric carbon, then it is called as D isomer. If the position of OH group is to the left of asymmetric carbon, it is called L isomer. Okay. Now, this D and L is just giving you the absolute configuration. That is just the position of OH to the right of asymmetric carbon, to the left of asymmetric carbon. That's all it gives. Okay. It does not tell you anything about optical rotation. How much the plane polarized light is shifted. Is that clear? Through what angle it is shifted. That is not given by this D and L. Okay. That is why you say sign of optical rotation is not related to the absolute configuration. Okay. So D and L is only with reference to the position of a particular group attached to the chiral carbon. Now in this case it is OH group. Okay. OH to the right is D isomer, OH to the left is L isomer. Okay. D isomer may rotate the plane of polarized light either towards left or right. That can be understood only through experiment. Is that clear? D can rotate the plane polarized light either towards left or right. Now if the D isomer is rotating it to the right, then you will write it as D plus. And if it is rotating to the left, then you mention it as D minus. So this is an experimental observation. Okay. Now a mixture of two enantiomers in equal quantities, it will have zero optical rotation because rotation due to one isomer will cancel that of the other. And such a mixture is called racemic mixture, a mixture containing two enantiomers in equal quantities. It will have zero optical rotation, and such a mixture is called racemic mixture because one isomer will cancel the rotation of the other. And then this is one. Now here look at this example. Say this B, this is your nucleophile. Okay. Now when this B is lost, it is substituted by another nucleophile, say D. D is substituting B. So the position of D, if it is at the same position of B, then there is retention. That is, configuration is retained. The old nucleophile and the new nucleophile are at the same position. So it is retained. So the process is called retention. Okay. Now, if the D had come here, then it would be called inversion, because the new nucleophile is not retaining the position of the old nucleophile, but it is taking a new place, is it not? So that is called as inversion. That we will see. Now look here. Now remember SN1 and SN2 reactions of optically active halides. Now look at this halide. This is secondary in nature. When it is subjected to a nucleophile, say OH minus, then this OH minus, if it is an SN2 reaction, then where will this OH minus come? This OH minus is attached here. Br was to the right of carbon. OH is to the left of carbon. So this is inversion. Okay. Now why this is inversion? If you consider, after the loss of this Br, this carbon will be planar. That is for SN1 reactivity. For SN2 reactions, it is always accompanied by inversion of configuration. But if you consider SN1 reactivity, then a carbocation is formed, and that carbocation is always planar, and this OH minus could attack from the back, it could attack from the front. In that case, there could be both inversion as well as retention. Now look here. Now this is again a secondary one. In the slow step, a carbocation is formed. Now this carbocation is planar. Okay. Now this OH minus, this is the planar unit. Now OH minus could attack from the front. It could also attack from the back. If it is attacking from the front, then OH is here. If it is from the back, then OH is here. Now this product is the inverted product, and this product is the retented product. Okay. So remember, SN1 reactions are always accompanied by racemization. That is, both take place. Both inversion and retention take place. But if it was SN2 reactivity, then there is only inversion of configuration. Right? Because in the case of SN2 reactivity, there is no carbocation formation. Okay? Since there is no carbocation formation, there is no planarity, and planarity nahi hai to एक ही चीज पॉसिबल है, दैट इज इन्वर्जन.